In today's video, we're going to be looking at parallel circuits in terms of wiring igniters in parallel, because this catches a lot of people out. So usually there's some common issues when it comes around fireworks, usually around talons. So the first problem with talons normally is that people treat them like E-matches and wire them in series, and then one fires but none of the others in the line fire. And that's the way that the talons have to get really warm. So they need to keep a current flowing through them for quite a while before they actually ignite anything, unlike standard igniters, E-matches, where obviously there's a pyrogen material there that just needs a small amount of heat to get it to pop. So wiring talons in series is a #1 problem. So people often go, well, that's okay, I've learned from that, I'll wire them in parallel, that's fine, I'll be perfectly okay. And they're not, because they don't realise some of the downsides of parallel wiring, and we're going to discuss that today. Other issues I've often heard about is people connect huge amounts of cable with E-matches in series and it doesn't fire, and that's because circuit resistance is too high, and we'll discuss that in a few videos. But that can commonly also be caused because continuity checks out properly, because continuity doesn't necessarily always check resistance, it's just checking for a complete circuit. So unless your firing system will also check for a complete circuit, for a resistance, sorry, then you'll find it'll just say it's okay, even if it's got a very, very high resistance. And then lastly, I connected 5 E-matches in parallel and none fired, and this is due to a parallel current drop, which is exactly what this video is going to be about today. So let's quickly jump into it. So here we have a simple circuit. We have 18-volt firing system, which is going to be 2 PP3 batteries. We have 3 × 5 meter igniters, and we're going to say that the minimum surefire current for each igniter is 500 milliamps or bigger. Now, on the diagram you can see we've got 0.26 ohms, which is the cable resistance, so that's 5 meters of the AWG cable for the igniter. So we have 2 of those because we've got 5 meters either side of the igniter, haven't we? So we've got 10 meters of cable in total, plus the 1.2 ohms, which is the head of the igniter. That little fuse wire is about 1.2 ohms. So we've got that by 3 in parallel. So to work out what the total resistance is of this circuit, we simply would use Ohm's law in series, but we have to slightly change Ohm's laws to figure this out in parallel. It's simply 1 over R total equals 1 over Rn. So you effectively do 1 over R1 plus 1 over R2 plus 1 over R3, and that will give you your total. So if we now look at this circuit in more of electronic form, so we've just added all the resistors together to make effectively the resistors, rather than have 3 separate resistances, we just pull them together into one. So now if we calculate on this, we'll find that 1 over 1.72 plus 1.0172 plus 1.072, etc. will equal 0.57 ohms. Now, if we can use Ohm's law to figure out what the current can be from this circuit. So we're now getting 18 volts over R, which is 0.57 ohms, and we're getting 31.57 amp, which, if you are aware of the chemistry of a 9-volt battery, it doesn't sound particularly good, but we'll keep going with this, because quite often you'll find the next part is that then people will do V over R again to work out the branch current. So in this case, we get 10.46 amp across each branch, or through each branch. So, okay, so we've divided basically the total current by 3 because our resistances are equal. Now, we can already begin to see where this is going wrong, because this won't happen. Why? Well, first of all, we need to make sure the current per branch must be larger than the igniter minimum surefire current to guarantee firing, and according to our calculations we're fine. We've got over 10.46 amps going over each branch, going through each branch. Well, yeah, we haven't, though, have we? But we'll carry on and we'll see what happens next. So then we have unequal resistances. So this is where obviously the current will not get split equally. We're going to have different resistances per branch. So in this case, we're looking at a 5 meter, a 10 meter, and a 20 meter igniter. So the resistances get larger on each added circuit. Again, we can use the same formula, but again, we're going to convert it into an easier circuit to look at. And now we've got 1.35 ohms in total if we were to look at the total resistance. And again, if you apply into Ohm's law, we've now got 13.33 amp, because we've got a higher resistance, obviously. And then if we do our same trick again and we divide that over the branches and we do Ohm's law, we get 10.46 amp on the first one, 7.37 amp on the second one, and 6.52 amp on the last one. And alarm bells should already be ringing in your head right now, because you've got three currents that, if you add them together, do not make 13.33 amps, which is what the total current you've already worked out on with Ohm's law. So where have we gone wrong? What have we done to cause this problem? Because this is a really common issue that some people figure out, and they don't necessarily think about the next step, which is it actually possible? They just think, oh, the numbers look good, I'll be fine. So we need to first of all think about how batteries work and their current peak, because that's what we're interested in. When we fire a system, generally we're trying to short the battery. Well, not completely short, but basically short the battery. And with the 9-volt, this chart is going to be very, very estimated. It's very difficult. The manufacturers don't really give you these sorts of details. You'd have to test the batteries yourself to figure this out if you wanted to get really accurate numbers. This chart is from the Cobra website, by the way, in terms of how they've worked out series and parallel. So first of all, if you look at the 9-volt battery, they're saying you can get 10 E-matches in series, which sounds good. You can only get 4 E-matches in parallel, and you can only get 2 talons in parallel. Now, obviously, talons are higher resistance than igniters. So an igniter, you're looking at probably about 1.8 ohms each, say 2 ohms to be safe. Talons, you're looking at between probably 7 to 10 ohms each. So much higher resistance. So if we look at the peak current from a 9-volt battery, we're only looking at about 1 amp peak. That is all. And just because you've got 2 batteries in series makes no difference to that. Yep. If you wanted to increase the current capacity, you'd have to put them in parallel, but then you'd also only have the 9 volts. You wouldn't be able to have 18 volts if they're in parallel. And if you look down the line, so for example, like their 14.8 volt LiPo, I reckon would be about 2 amp peak. And then by the time you get to the bottom 3, which are all pretty much lead acid batteries, if you're looking at the 12 volt ones, you can get some ridiculous sized batteries which have horrendous peaks. And if you look in the data sheet, it's really scary, because if you actually did short the batteries, so much current would flow, you'd melt pretty much everything that's connected, including the battery. So when you get into lead acid batteries, you've got to be really careful how you handle them, because if you do short them out, then it's very easy to make them explode or cause a fire, etc. But anyway, back to our 9-volt example, which we now know is about a 1 amp peak. So if we now look at our circuit again and we redraw everything out, everything's gone a bit slow. So what I'm going to do is I'm going to do the 1 over R for each of the branches. So 1 over 1.72 is 0.58, 1 over R2 is 302, and so forth. Now, rather than just do Ohm's law, I'm going to slightly change Ohm's law. I'm going to do the branch resistance divided by the total parallel resistance times the current we know we can supply. Now, if you do that per branch, you get 3, obviously, currents. So we get branch 1 is 0.43 amp, branch 2 is 0.30 amp, and branch 2 is 0.30 amp, and branch 3 is 0.27 amp. So if we were to add those up, we would get our 1 amp. So we know we're okay here. That is our maximum current we can supply to this circuit. We know that all of these will be 18 volts because they're in parallel. But we can see that actually now we have a much larger issue here, and that is that the current per branch must be larger than the igniter minimum surefire current to guarantee. We've said that our surefire current is 0.5 amp. None of our branches reach 0.5 amp. So we have too many igniters already in parallel. So where we could have put, for example, 10 possible E-matches in series, we can see we can't even get 3 E-matches in series using these wires and these resistances. So that's food for thought there, that sometimes people get carried away in believing that you can put endless amounts of igniters in parallel because they do the Ohm's law over it, and they get some ridiculous values that their power supply can never supply, and they believe they're safe. So just be careful. We have to be really, really careful when we do parallel circuits. Now, people often say, oh, you shouldn't wire in parallel, you should wire in series because you wouldn't have this issue. And some people that wire in parallel would argue that usually, even if the circuit is broken somewhere, something will fire. Some effects will fire because you can't break every branch, which is a really good point. They also say that all the igniters receive the same voltage, which is true. And obviously, if in terms of talons, if one talon fires quicker than another, it won't stop the others from firing because it only breaks its own branch. The cons of this, though, however, are that if you have a very low resistant branch, it obviously steals more current than the other branches. So you'll effectively have less current over the higher resistant branches. Equally, if you're firing more than one Q on the firing system at once and your firing system does not cap the amount of current, it doesn't have a current limiter in the Qs, you could potentially get into a current thief scenario where a low resistance Q will steal all the firing current from any other Q that's firing. So you only get one Q that fires. Obviously, this is more difficult to calculate if you're unaware of how to figure it out. And obviously, less igniters can be fired in parallel than in series. So there's pros and cons to both systems. And you just have to look at the scenario that you're going to use it in and whether or not it's appropriate. For lots of live event work, you will find parallel wiring is very common, particularly if you're on like a televised show, for example, because you would want at least something to go rather than nothing to go. But you'll find a lot, often in firework fields though, series is more commonly used. So, it's up to the end user to decide what they're going to do, but you just need to be aware of the pros and cons.